Alright everybody, welcome back to another video. Here we're going to be talking about one-sided limits and continuity. You might ask yourself, what's a one-sided limit? Well, it's a limit, but from one side. Let's make that kind of concrete with a good example. Kind of our workhorse limit, honestly. Let's let f of x equal 0 for x less than 1 and 1 for x greater than or equal to 1. Alright, making our graph. Sounds like this where I wish copy paste was a real life tool. Actually, I wish that quite often, but alas, my dream will go unrealized. Probably. Who knows what scientists will come up with in like 50 years. Okay, this is our function f of x. And we said, hey, the limit as x goes to 1 of f of x does not exist. D&D. Okay, yeah, that made sense, right? Because there's this big jump here that we can't reconcile. But the problem was just the jump, right? It works on either side. And it would work if I was only going from one of the two sides. It would be fine. It would work out. Let's see if we can quantify that. We'll write that the limit as x approaches 1 plus, meaning from the right side, everything bigger than 1, of f of x. Well, as long as we're talking about things bigger than 1, f of x is just 1, right? That's what it means. We're in this range. And the limit of constant is just a thing. What about the other side? Limit as x goes to 1 from the left. Well, if we're only talking about things less than 1, we're always in this first branch. So limit as x goes to 1 from the left of f of x is the limit as x goes to 1 from the left of 0, which is just 0. And that is all a one-sided limit is. Is it saying, hey, what if you approach from the right and approach from the left separately instead of approaching both together, which is what a normal limit does. Formally, our definition of a right-hand limit or a right side limit, approach from above limit, different textbooks will use different names. The limit as x goes to a plus. This is the notation we'll use, and this means limit as x approaches a from the right side of f of x is equal to L if f of x gets close to L as x approaches a from the right. Left-hand limit definition, similar. Yeah, all you would do for the left-hand limit instead of that is say limit as x approaches a from the minus f of x. So that's our notation, same idea. You're just approaching a from the left instead of from the right. Okay, so how do these two things relate to normal limits? Since for our example with the step function, we seem to have both of the one-sided limits, but the actual limit didn't exist. Well, what we're going to say is actually a theorem. It's a very nice theorem. The limit as x approaches a of some function f of x is equal to L if and only if the limit as x approaches a from the right side of f of x exists and is equal to the limit as x approaches a from the left side of f of x, and they're both L. So as long as both one-sided limits exist and are equal, we get that the original limit will exist and be their shared value. For example, this is going to be our only way, really, to calculate the limit of piecewise functions at the point where they switch from one branch of the function to another. Let's let f of x equal the piecewise function x squared plus 4 when x is greater than or equal to 0, and negative x plus 4 for x less than 0. The limit as x approaches 0 from the right of f of x is the limit as x approaches 0 from the right of x squared plus 4, which, applying your limit laws, again, that'd be a good exercise, is to write out these dot dot dots explicitly. We'll give you 0 squared plus 4, aka 4. Now let's talk about the left side limit. Limit as x approaches 0 from the left side of f of x is the limit as x approaches 0 from the left, since we're always less than 0 when we're approaching from the left, we're always going to be in this branch of the function. Negative x plus 4, which is the limit as x approaches 0 of negative x, which is the same as negative limit as x approaches 0 of x, plus limit as x approaches 0 from the left of 4, which is 0 plus 4. 4 again. So both limits exist, and they're equal. Specifically, they're equal to 4. So, limit as x goes to 0, not plus or minus, just 0, of f of x exists and is equal to 4. Now, these techniques only really useful for calculating limits of piecewise functions, but they're really the only way to effectively calculate the limits of piecewise functions. So it's nice that we have them, because piecewise functions come up a lot, especially in business things where you might be using one pricing strategy and then another pricing strategy if supply is at a certain point, etc., etc., etc. All right. So that's one-sided limits, but this section is called one-sided limits and continuity. What does continuity have to do with limit? You might have heard that a function is continuous if you can draw its graph without lifting your pencil from the paper, which, kinda, but not really. It's good enough for most high school applications, but you're in college, we're going to give us a little more robust definition of continuity. So, a function is continuous at a point A if, so now continuity is a point where a function can be continuous some places and not others. And it will be continuous if three things happen. First, we need that f of a exists. If the function isn't defined there, it doesn't make sense to talk about it being continuous there. So that's a reasonable first condition. Secondly, we want the limit as x approaches a of f of x to exist. Again, a reasonable criteria, because a function like this should not be continuous there. How do we snipe that it's not continuous there? By checking whether the limit exists. So our third condition is that we want the limit as x approaches a of f of x to not only exist, but we want to equal f of a. Okay, why that condition? Well, that function we defined way back when, the one that was x squared everywhere except at 0 and then it was 1 here, shouldn't be continuous here. The f of 0 exists, the limit as x approaches 0 of f exists, but they're not equal to each other. So this function is not continuous because it violates condition 3. Okay. Continuous functions play really nice with limits because by definition, if you have a continuous function, a function you already know is continuous from some other thing, to find the limit as x approaches a of the function, all you have to do is plug a into the function. Which is really handy because it means you don't have to sit through sifting through limit laws. Now, to do this, you have to know already that the function is continuous. If you don't know that, you're out of luck. But if you do know that, then you're home free. So, what are some functions that are continuous? Alright, I will state these without proof. But these are some properties of continuous functions. Two most important functions to have continuous, and these ones we should all agree are continuous. Constant functions are continuous. Right? Agreed? It's just a horizontal line. So I think we should all be content with that. Proving it, not hard, but work that I'm not going to write out. Do it yourself as a fun exercise. Also, f of x equal to x is continuous. Again, something we should all be content agreeing to without proof. Be fun to prove it yourself if you want, though. So those are two things that we're going to all agree are continuous. Now, let's say we had two continuous functions. Also, these are continuous everywhere, not just at a specific point. Now, if we have two continuous functions at a point, then we get a whole slew of other continuous functions. First, f of x to the r is continuous at a. For all r in R where f of x, or sorry, where f of a to the r exists. Alright, what does that mean? You can raise a continuous function at a point to whatever power you want, and it'll still be continuous there, as long as it doesn't give you like a 12 divided by 0 kind of a situation, right? So that's all well and good. Both of my erasers ended up on the floor again. Alright, we also get a few more continuous functions. F plus g is continuous at a. Also, f minus g is continuous at a. So that's nice. Adding continuous functions together gives you a continuous function. Similarly, multiplying or dividing continuous functions is continuous. As long as g of a is not equal to 0, because then you would have a divide by 0 error. Gluing all of these properties together yields the following theorem. Polynomials are continuous everywhere. And let's think about why that is. Well, if x is continuous, and now x to any integer power, positive integer power, is continuous, constants are continuous, if I can add together continuous functions, that's all the parts of a polynomial, right? Because a polynomial is specifically a sum of x to natural number powers and constants. So those will be continuous everywhere. And rational functions which are a polynomial divided by another polynomial. Think like x cubed over 4, or x to the 7th plus 1 divided by x squared minus 3, stuff like that. Polynomial over polynomial are continuous, except at the zeros of the denominator. right? When the denominator is 0, divide by 0 error, can't do it. But everywhere else, if polynomials are continuous everywhere, then we can divide and everywhere it'll work, except at the zeros, the denominator. So those are two really nice facts, which you should have seen in pre-calc, but if not, here they are. And this gives us one more cool thing. Two more cool things, actually. One of them is really short-lived. First cool thing it gives us, we can compute limits for rational functions and polynomials almost instantly. Let's find the limit as x goes to 72 of x to the 29th power minus 4x to the 17th power plus 4, and the limit as x goes to 1 of x to the 36th minus 3 over x squared minus 9. Alright, first limit. Well, this is a polynomial, so it's continuous everywhere. More specifically, it's continuous at the point we care about. X equals 72. So, the limit as x goes to 72 of x to the 29th minus 4x to the 17th plus 4 is 72 to the 29th power minus 4 times 72 to the 17th power plus 4. And I'm not going to compute that because those are some very large numbers. But we know what that limit is, so that's nice. Okay, let's compute the other one. I like this chalkboard a lot. My only complaint is this little shelf here for holding chalk and erasers, not wide enough. Okay. Second one, x to the 36th minus 3 over x squared minus 9. Okay, that's a polynomial. That's a polynomial. Is a rational function. The zeros of x squared minus 9, so the zeros of the denominator, are x equals plus or minus 3, which is specifically not 1. Right? How do you find the zeros? Factor. Okay, so cool. We're evaluating the limit at a point where the function is continuous. So this whole mess is continuous at 1, hence the limit follows easily. X to the 36th minus 3 over x squared minus 9 is 1 to the 36th minus 3 over 1 squared minus 9. 1 to the 36th power, just 1. 1 minus 3 is negative 2. Here we have 1 squared, which is 1, minus 9, negative 8. Negative 2 over negative 8 is positive 1/4. How about that? Okay, so we can compute limits like that easily. And continuous functions satisfy one more very important theorem, called the intermediate value theorem. It's one of the crowning achievements of calculus. I will not prove it here, but you can find the proof in most textbooks. I'm not sure if ours has it. It's kind of complicated, but it's a very important theorem. So we will see. All right. The intermediate value theorem. States that if we have some continuous function f, and it's continuous on the closed interval a to b. So it could be discontinuous outside of there. What we're caring about is on this interval, and it's continuous on that interval, so everywhere inside of it. If f of a is strictly less than c, strictly less than f of b, there exists some d in the open interval a to b such that f of d is equal to c. Let's see what's going on there with the picture. So we have our function f, and it's clearly continuous on this interval, a to b. Great, we satisfy the theorem. What do we get? I'm going to pick a point C that's between f of a and f of b. Right? Because there's a gap between f of a and f of b, I can pick a number between them. And what this tells me is that I'm guaranteed that there exists a d in between a and b such that c is also f of d. In fact, there's multiple points for this c, but if I picked maybe c up here, right, then there would have only been one. Yeah, so that is what the intermediate value theorem states. Colloquially, what this means is a continuous function has no sort of jumps. And that makes sense. And that's where you got that definition way back of a continuous function is one that you can draw without lifting your pen. The intermediate value theorem is actually what guarantees that that's the case, not continuity. Alright, so most important application of the intermediate value theorem is for zeros. Let f be continuous let's say it's continuous on a to b. Suppose f of a and f of b have opposite sign. Or opposite signs, I guess. I think both are grammatically correct, but who cares? This is a math class, not an English class. Okay, so what does this mean? It means say f of a was positive and f of b was negative, or the other way around. then f has a 0 somewhere in the open interval a to b. Our picture for that, let's say we have our function f on our interval a to b, and f is a continuous function there. I know that f of b is greater than 0, and f of a is less than 0. Other way around would have worked too. I know that there has to be a 0 somewhere in there. And in fact, here's the 0. So that's pretty important because finding roots is a mathematically both interesting and useful problem. It'll have a lot to do with optimization, which we'll see later. I think that's sections 4.3 and 4.4. So we'll be covering those later in this course. But yeah, this is going to be an important fact that will come up again later. All continuous functions have that property. Okay, I think that's all for now. Have a great rest of your day.